With population curves, there are a couple different types of population curve. Generally, if we assume a population is growing from zero, it can grow really fast over the course of time. And most population curves have what we call an exponential phase at the beginning, where we see exponential growth. At that point, there are a couple different things for what the curve can do. The curve can keep growing exponentially but it can't grow exponentially infinitely. It can keep growing until resources start becoming limited. And when resources start becoming limited, growth slows and eventually it'll level off. This point where it levels off is what's known as the carrying capacity. And the carrying capacity has a precise definition that you need to know. Carrying capacity is defined as the maximum population that can be sustained in a given ecosystem for a period of time. So it's not just maximum population, it's the maximum population that can be sustained. And the reason I'm saying that is because sometimes the population can shoot over the max. And then it might come down and it might sort of oscillate around some value. And that value that it oscillates around is known as the carrying capacity. This point here is shockingly called an overshoot, where the population grew too high, higher than could be sustained, and some died off. This type of curve is known as an S curve because of its S-like shape. This type of curve is known as a J curve because of its J-like shape. The J curve can then turn into an S curve, or another possibility is what we saw in the predator-prey, where the population shot up and then crashed, and then the population shoots up and then crashes. So in this type of situation, we get a repeating J curve. And this is typical of fast growing populations. So like R strategists, this is typically pretty common. So your R strategists, again, are the ones that reproduce really rapidly, like rabbits. One of the things you may be asked to do with population curves is do some calculations related to them. So this is a curve of, I don't know, I think I looked up like the population of Canada. Suppose we want to find the change in population from 1890 to 1970. 1890, 1970. The first thing I'm going to need to do is I'm going to need to approximate the value for each one of these. Bringing this over to my y-axis, it looks like the population's about 5 million here. And in 1970, if I I would estimate about 22.5 million. So the command term calculate means you need to show your work. So 22.5 minus 5 will give me my change of 17.5 million. Percentage change in the next part is going to ask me to do something different. Percent change is going to be the difference compared to the initial value. And now I'm being asked from 1930 to 2010. Okay, so from 1930 to 2010, it looks like it goes from 10 million to 35 million. My change is 35 minus 10 over my initial value of 10 times 100. So 25 over 10 times 100, and the population changed by 250%. The last thing you could be asked to do is the percent change per year. And in each case, make sure you're reading the question carefully. So I already found the percent change for this time period. Percent change per year is going to be the percent change divided by the number of years in the time interval. So 1930 to 2010 is 80 years. So 250 divided by 80, got to use my calculator now. I think it's, yeah. It's going to give me an answer of 3.125 percent per year as an answer. You want to make sure that you're putting units on your answers as well. Okay, so we have a couple problems for you to try. You're going to practice calculations and you're also going to practice some explanations. Do your best with the explanations. You might not get them fully right, but do what you can.